All right, today's topic is volcanoes, and this will be the first of a two-part set of videos. So we'll label this one Volcanoes number 1. And today is going to be all about eruptions. In your textbook, this is chapter 4. And what I need to do to start this is we need to make sure that we're on the same page when it comes to petrology and magmas. So what you need to recall from past lectures is the concept of extrusive, where lava reaches the surface, and the textures that are produced by that, right? Fast cooling rates. You also need to remember rock names for that extrusive texture, and the rock names here are basalt for the mafic composition rich in magnesium, dacite for intermediate, and rhyolite for felsic. Now, one thing I do recognize from my last lecture is I did not teach the word andesite. And sometimes professors choose to teach intermediate as andesite. So in this class, we're just going to keep those two together. That's the first thing you need to recall. The second thing you need to recall is the definition of the word viscosity. That is resistance to flow, and it's controlled by molecule length. Viscosity is huge for volcanic eruptions. The explosive, dangerous ones are high viscosity. The gentler ones have low viscosity magmas. And then the third thing I need you to recall is the word volatiles. Volatiles. And this refers to anything that was a gas, that can be a gas at the Earth's surface. H2O, CO2, sulfur are different volatiles that occur dissolved in magmas. And these, when they exsolve, like when you shake a Coke bottle very hard, you get all those bubbles. That's exactly what these will do. These make bubbles, and bubbles are important for all aspects of volcanic eruptions. In fact, we should do a graph right here, and this would be the start of new content. And what we're going to do in this graph is we're going to look down into the subsurface like we often do in this class, and we're going to plot the amount of H2O that can be dissolved inside of a magma as you go to greater depth. All right, these are our axes, and learning axes in an intro science class is so important. So let's go 3 kilometers, 6 kilometers, 9 kilometers, 12 kilometers. All right, so we're in the shallow lithosphere, and our water contents will go 2, 4, 6, and 8. The absolute numbers here don't really matter, but these are close. The curve we need to put in is right here. And what this curve represents, it's solubility. So let's see what I mean by that. Solubility means dissolvability. And so what this line tells me, at 3 kilometers depth, solubility says the magma can have, what do you think that is? Like 3.5 weight% H2O dissolved in it. And if you have any more H2O, let's say at 3 kilometers depth you have 6, well, it can't all be dissolved. And so the side of the line to the right is the production of bubbles and pumice. And if you have a situation to the left of the line, there is no bubbles because you're undersaturated in your volatiles. Everything that is there is dissolved. But track with me the path of a volcanic eruption in terms of depth. Where do magmas start? They start deep down. And then they rise through a conduit or a dike towards the Earth's surface, right, vertically, and they're going to cross that line. And so there is a situation that occurs during eruptive ascent of a magma where we cross the line and therefore bubbles start to form. And so if we were to like draw what the conduit looks like as we cross that line, it would be something like this. Here's our conduit, and when we're below the line, there's no bubbles. And as we reach the line, bubbles nucleate. And as we go higher than, okay, so like 1 would be, or I could have done A, but there's 1, and then here is 2, which is right at the crossing point. And then by the point of 3, we're like growing and making bubbles, right? And then we're at 4, we're near the Earth's surface, there's like very little pressure. Those bubbles have had a chance to really grow. And so you're at 4, we've made a pumice, and the volcano is likely to erupt pretty explosively. That's the concept of, we could even write this, more bubbles in magma at shallow depths, because it's controlled by solubility. That's one of the key words, I guess, today. So with this into consideration, I would like to now talk with you about two types of eruptions. There are effusive eruptions and explosive eruptions as these two main categories. And effusive eruptions are the passive ones, the gentle ones, the ones that do not explode. And we'll define this here as, and I'm using the word peaceful. We could put that in air quotes if you like to. For a volcano, it's peaceful. Compared to taking a nap, you know, it's a pretty dangerous thing. But this is the peaceful oozing of lava. And it can be any composition. One thing that is critical to state with this is that bubbles were made. They have to be made during ascent. But in the effusive scenario, they escaped. And I'll sketch that here. So what I'm talking about is, here's our conduit again, like we did before. Bubbles start to nucleate, bubbles start to grow. But in this situation that produces effusive eruptions, the gas actually like escapes out of the conduit so that bubbles do not exist as we get to shallower depths. And so we'll label this, we could say gas escapes, we could say bubbles collapse, and the key to this is slowness. In order to allow bubbles to escape, the magma must ascend slowly or be very low viscosity. So here's our two conditions for effusive eruptions. They are either low ascent in conduit, or they are low viscosity melts. And the reason why both of these work is if you're slow ascent, then the bubbles have time to escape. So we could say allows escape of bubbles. And if you're really low viscosity melt, the bubbles can move really easy, right? Because the melt doesn't resist flow. And so the bubbles are allowed to escape. And sometimes this is an and/or situation where magma is ascending slowly and it's low viscosity. And so those are going to be the situations that allow for effusive eruptions. This tends to occur at the end of an eruption. So tends to be at end of eruption. The power of an eruption starts early, and then as the pressure in the chamber relaxes, the magma ascends more slowly, gas has time to escape. There are felsic, intermediate, and basaltic lavas to discuss. And we're going to say here basaltic lavas. You could write that mafic if you'd like to. And then the felsic to intermediate, they have different shapes. And they have different shapes because of their viscosity. So we could say the shape of the lava flow is viscosity controlled. If we have a basaltic eruption, here's the conduit. Here is our eruption surface. Let's do that over here too. Here's our volcanic conduit. Here's our eruption surface. The form of these two lavas will be different. In a basaltic lava, it will ooze out and just stay as a very thin sheet as it covers the land. Whereas a felsic to intermediate, this will actually stack up and be unable to flow very far. And you end up getting this really jagged, thick, ugly lava dome. Very vastly different shapes. And so this is for our dacites, our andesites, and our rhyolites. The words associated with felsic to intermediate would be things like thick, steep, high viscosity. The descriptive term is a lava dome with sides that are thick and steep. They typically sit at the top of volcanoes or maybe near the base, but anyways. Okay, now for basaltic, these are thin. And there's two different types of these low viscosity basaltic. One is called A'a, the other is called Pahoehoe, and it has to do with the surface texture of the lava. A Pahoehoe is a basaltic lava that is smooth and maybe you could say ropey texture on the surface, and then A'a is this crumbly tank tread kind of moving lava flow. Crumbly tank tread. All right, let me insert some pictures here just so you can see some real life examples. Here's a lava dome from a volcano in Indonesia, and here are some lavas. And let's highlight a couple of things we need to see here. There's the crater of this volcano, so you can imagine the conduit is somewhere down there, and it's this jagged, rubbly shape that's barely able to move. That is our lava dome. Now in this picture on the other side, we have Pahoehoe here at the base. You can't see that too good, but see that P? This is referring to the Pahoehoe part of the picture, and this more crumbly bit that's overriding it, that is the A'a type of basaltic lava. You can search for videos on these and watch how they flow on YouTube, and I would recommend that. So, if you do not allow your gas to escape, then the volcanic eruption is explosive. And there's 5 types of these to go through. This lecture might get a little long. So we got a list of 5. The explosive eruption styles. There's actually 5 of these, and we're just going to go through them one by one and talk about the gas in them. The Hawaiian eruption style is a gas jet. It's actually like 99% of it is essentially gas with blebs of lava, molten lava spewing out. These tend to be weak. They tend to not be very explosive. They're associated with mafic compositions. And when they do erupt, they produce ash and spatter. A sketch of a Hawaiian eruption column or a conduit might look something like this, where it's just huge amounts of gas, like 70 to 1 in terms of our gas versus melt ratio. And so almost this whole empty thing is just gas, and then there's little droplets of lava that are being blasted through as liquid blebs. A picture, you might say. Sir, well, here you go. Here's a Hawaiian explosive eruption. Look at the amount of magma glowing incandescent. Sorry, lava. It's actually so much gas. You just don't see the gas. And you can see how it's collapsing down and making a lava flow. This picture is from Hawaii, and that's where the name came from. All right, our second type of eruption style is more explosive, and we're doing a list in that order. We're going from least explosive to most explosive, and so the next most explosive is a Strombolian eruption style. And here we've got these bubbles, lots of little tiny bubbles that join up with other bubbles and coalesce to make bigger bubbles. So we're going to say bubbles coalesce to make big bubble slugs. To draw that, here is our conduit. And so we've got these little bubbles, and they're growing and they're mixing in to make larger bubbles, and those larger bubbles make larger bubbles, and all these bubbles are rising to the surface. And so when one of the bubbles reaches, like, let's say the top, it pops and it shoots stuff into the air. Stromboli is what this name is named after, which is a volcano in Italy. And these are also weak. They only are going to shoot things like kilometer scale. So if you're a few kilometers away, you're going to be pretty safe. They are associated with mafic magmas. All right, so this is for this basalt as well. And the things that this is producing is ash and like little pellets, which we call bombs. A picture for Strombolian eruption. Here's a good example. And what I want you to picture as you see these incandescent like fireworks streaming out with ballistic trajectories, this is one single bubble, a big bubble, as big as a classroom, let's say, that has popped. And it's sending the bubble wall fragments along these pathways where they land as little bombs glowing in the dark. All right, number 3 is now so powerful that this can start to get dangerous. This is the Vulcanian eruption style. And these are defined as discrete cannon-like blasts. And with a discrete cannon-like blast, we need to build up some serious pressure. So what we have in the Vulcanian style is the top of the conduit gets plugged, maybe by an avalanche or frozen magma. And so all the bubbles that are rising up get trapped underneath this cap until there's so much bubble pressure underneath and buoyancy from that gas that it can't stay under the plug anymore, and so it just it explodes through the plug. Let's say that the bubbles explode through the plug, which has capped the conduit. It will send material on the order of a few kilometers, and the explosion is local. We're going to say that. When it does erupt, it produces chunks of the cap that are called blocks, and then fragments of magma that are called bombs, and then all the really fine stuff, which is ash. The other thing, I guess, let's put into this drawing even, is we're going to put some curved things here at the top. These are shock waves. The explosions here now are powerful enough that shock waves are released when the cap disintegrates. A picture of a Vulcanian blast is here. And what you're going to see different, besides the time of day so we don't see the incandescence, I would like you to see with me how much ash there is in this column. And look at, see these little specks and dots? Those are fragments of the cap that are raining down. It could be dangerous if you were a volcanologist standing here studying the volcano. All right, and then the final of our explosive styles is called Plinian. And these are the eruptions that I think most people think about when they think about volcanic eruptions. And we'll just go ahead and start with the picture of Plinian. This is when the big volcano produces an eruption column that rises from the vent, eventually reaches a level where like buoyancy is reached with the atmosphere, and it spreads then by winds blowing the ash downwind. This is the quintessential volcanic eruption. So the reason why the Plinian eruption column works, or the Plinian eruption happens this way, and it is by far, we're going to say like the most explosive. No energy or little energy is lost from bubbles because the melt and the bubbles stay fully coupled. There's no escape. Melt and bubbles stay coupled. And because they stay coupled, the bubbles don't have a chance to escape. All the energy stays in the system, and when the bubbles burst and they rip through the bubble walls holding together, the gas is able to expand, and it can do that explosively. Let me try to, I'll read that and write that here. We're real close to the end of this lecture. We'll say, growing bubbles eventually grow so thin with the walls. Let's see, growing bubbles rip apart their bubble walls. That's a good, I like that. Growing bubbles rip apart the bubble walls, and gas explosively expands. And the released gas from the bubbles explosively expands. And this is what creates all this energy that makes the power and explosivity of the Plinian style. And it produces, so let's say what it produces ash. And we see that ash in tall eruption columns. And we have this thing at the top of that, which is called the umbrella region, which is ash being blown by the wind. They can move very long distance, which makes them more of a threat for a variety of different reasons. We should draw what the conduit looks like here before we finish this lecture. So here's our conduit, and magma is rising, and bubbles are forming, and the bubbles are growing until the point where the bubble walls get so thin, my bubbles here are kind of sloppy, that fragmentation occurs, and the magma rips apart. Fragmentation is popping, all right? That's another way to say like the bubbles are popping. And then we just get gas and ash moving super fast up the conduit the rest of the way as this dusty jet mixture.